So when we're trying to determine how ions are made from the periodic table, we do need to take a look at this line right here, and I'm kind of drawing this in, and then you can't really see it, and it's invisibly there. This is called the stair-step line, or well, you can pretty much call it anything you want, but this is the line that determines um, if it's a metal or a non-metal. Excuse me, I'm having a hard time ending it where it's supposed to end. It's supposed to end right there. And all of the elements that are to the left of this line, okay, are considered metals. And all of the ones that are to the right of the line are considered nonmetals. So now, why do you ask, is it important to know whether it's a metal or a nonmetal? And that's a great question. Now, some of you may know that elements that touch this stair-step line are called metalloids, and there is that third category. So there's metals, nonmetals, and metalloids, and boron and germanium and antimony and beryllium and polonium. Those are all metalloids. And for right now, we're going to just disregard metalloids for right now. We're primarily talking about metals and nonmetals. And it is important to know whether an element is a metal or a nonmetal. And the reason for that is based on whether or not it loses electrons or it gains electrons. So let's discuss here what's happening if an element is a metal or a nonmetal. Well, if it's a metal, it tends to lose electrons. Okay? And if it's a nonmetal, it tends to gain electrons. Okay, so metals lose electrons and nonmetals gain electrons. So let's take a look at group 1A, the alkali metals. Okay, and here we have group 1A, the alkali metals, and if you recall, as I said earlier, group 1A only has one valence electron. Well, everybody on the periodic table wants to have the same number of valence electrons as the noble gases. Well, these guys have one, and so let me show you what hydrogen looks like. Here is the nucleus of hydrogen, and in its first energy level where the electrons are stored, it has one electron. So as you can see, hydrogen has one valence electron. Well, here's lithium. Okay, here's a picture of lithium. Move it out of the way. And as you can see here, in the center there are 3 protons, 4 neutrons. In the first ring, in the first energy level, there's 2, but look on the outside. The outside electrons are called the valence electrons, and there's only 1. And here is sodium. Just take a look there. Look on the outside, and you'll see that there is 1 electron on the outer ring. Okay, and the same is the case for potassium, rubidium, cesium, and francium. They all have 1 valence electron in their outer ring. That's why they're in group 1A. That 1 means 1 valence electron. But they're all metals, so they're going to lose electrons. And the electron that they're going to lose is they're going to lose the outside valence electron. And when they do that, that gives them a stable configuration. Okay, so when sodium loses that 1 outside valence electron, it has these inner ones here to keep it stable. Now, hydrogen really doesn't want to lose one. The reason hydrogen is put into that group is because it has 1 valence electron, but hydrogen typically wants to gain 1 to be like helium. When it gains 1, it has 2 outside electrons, just like helium, and causes it to be stable. But everybody else wants to lose 1. Hydrogen is the only exception. He actually wants to gain 1. So this guy right here wants to gain 1. But all of these right here, these guys all want to lose 1. Okay, we're talking gaining 1 electron and losing 1 electron. Okay. So let's talk about what happens when an element loses an electron. So let's consider the group 1A again. And let's go with, I like to use my personal favorite. I like to use sodium. So let's just talk about sodium. And we're talking about Na here, and it has one valence electron, and I'm going to indicate that by putting a blue dot here on the outside. Okay, so most of the time chemists are only concerned with using valence electrons, because valence electrons again are responsible for chemical reactions and chemical bonding. Okay, so this valence electron, sodium wants to lose it. So if we look at a neutral sodium atom here, a neutral sodium atom, and you know here atomic number 11 means it has 11 protons. Okay, and the atomic mass is roughly 23. So how many neutrons does it have? 11 plus neutrons equals 23. Well, 11 plus 12 equals 23. So it has 12 neutrons. Okay. And electrons in a neutral atom, it's also going to have 11 electrons. But remember, sodium wants to lose this electron. So this electron is actually going to get lost. And it's going to go somewhere specific, and I'll describe where it's going to go in a bit. But it's going to be lost. And when it loses an electron right here, this number is no longer 11. This number is now 10. Okay? And we have 11 positives, okay, and we have 10 negatives. So 11 positives and 10 negatives. And that gives me my overall charge. If I look here, this positive is bigger than the negative. So my answer is actually a 1 positive. So sodium, when it loses its electron, it actually has a positive charge. And so we indicate that by writing the symbol of the element and how many it's positive. And we don't have to write the number 1. We just assume that when there's a plus there, that it means 1 plus. And so sodium ion is this symbol right here, Na plus, indicating that it's lost 1 electron. And that is the same for all the elements there. So potassium ion, it wants to lose 1 electron. Lithium ion, it wants to lose 1 electron. Rubidium ion, it wants to lose 1 electron. So they're all indicated with their chemical symbol and a plus, indicating that they have lost 1 electron. So now let's take a look at the alkaline earth metals. Okay, and this is group 2A, alkaline earth metals. So the alkaline earth metals, these are group 2A. They all have 2 valence electrons. Okay, they all have 2 valence electrons. Okay, 2 electrons on their outer energy or their outer shell, and they're a metal. Okay, indicated that they're a metal, and they lose electrons. Okay, they want to give away their electrons to somebody that wants to take them. So this is group 2. Alkali metals, 2 valence electrons, and they lose electrons. And the same thing goes for group 3A. 3A has 3 valence electrons. Okay, and they lose electrons as well. And then group 4A has 4 valence electrons. I'm just going to do tick marks there. They can lose or gain, okay, depending on who they will form a bond with. They can lose or gain. Group 5A has 5 valence electrons. These elements only gain electrons. Okay. 6A has 6 valence electrons, and they also only gain electrons. 7A, the halogen group, has 7 valence electrons, and again, they only gain. And the the last and final group is the 8A, which is the noble gases. They have 8 valence electrons. They do nothing. They do not lose or gain electrons at all. They are what I like to call the Mary Poppins of the periodic table. They're practically perfect in every way. They don't gain, they don't lose, they don't readily bond with other elements. They don't go through violent chemical reactions, nothing. They are stable, and every other element on the periodic table wants to be stable like them. And the only way that those elements can be stable like the noble gases is by gaining or losing electrons. And so that is what all elements on the periodic try to do, is gain that stability by gaining and losing electrons. Now, how many they lose is based on what group they're in. If they have 2 valence electrons, like up here, the alkaline earth metals, they're going to lose 2 electrons. Down here, group 3A, 3 valence, they're going to lose 3 electrons because they want to have 8 in their outer energy level. They want to get rid of their valence. They either want to have no valence electrons or full valence electrons. So 4A is either going to lose all 4 valence electrons or it's going to gain 4. So they either can lose 4 electrons or gain 4 electrons. These guys lose 3 electrons. These guys lose 2. Okay. Group 5A, they're going to gain electrons. They want to have 8. So they have 5. They're going to gain 3 electrons. Group 6 is going to gain 2 electrons. Group 7 is going to gain 1 electron. Okay. And back there at group 1, just to reiterate, we covered that on the previous slide. Remember, the alkali metals, they have 1 valence electron. Okay. And they also lose 1 electron. So let's recap a little bit about valence electrons in the periodic table. Now I've got this little group here that shows the valence electrons of the periodic table. And if we take a look here, you can see that everything that is in group 1A, this is 1A right here, and that's the alkali metals. And if you take a look there, every element that's in there, hydrogen all the way down to francium, those have 1 valence electron. Group 2A, alkaline earth metals, have 2 valence electrons. We're going to skip these transition metals here, and there's a reason we're going to skip them for right now. Their valence electrons and how much they give up for forming bonds is quite different than the other elements. There's not really a fixed formula for them, so we're going to kind of skip them for now. Moving on to 3A, which is the boron group. We've got 3 valence electrons, followed by 4A, which is the carbon group, 4 valence electrons. 5A, the nitrogen group, 5 valence electrons. 6A, the oxygen group, 6 valence electrons. And 7A, the halogens, 7 valence electrons, followed by 8A with the noble gases that have 8 valence electrons, with the exception of this guy right here. This is helium. Okay. And helium is the only one that is in the noble gases that doesn't have 8 valence electrons. It only has 2. So that's a recap of valence electrons, how to determine how many valence electrons each element has based on looking at the periodic table.